introduce our next speaker, who will delve into the most mysterious and counterintuitive features of quantum mechanics. Professor Asiri Nanayakkara is a renowned physicist and educator known for preaching rigorous theory with accessible insight. Professor Asiri Nanayakkara is an honorary visiting research professor at the National Institute of Fundamental Studies. His research interests include electronic speech recognition and singular language processing. He has also worked as a computational scientist at Cray Research Inc. in USA before joining NIFS. Please welcome Professor Asiri Nanayakkara.
Morning, everyone. First, I'd like to thank the director of your press for inviting me to give this talk. Okay, the title, I hope you can hear me. Amazing and puzzling nature of quantum world. Outline. I will go through the outline very briefly. I will first talk to you about nature and reality, because we have to discuss it before we get into quantum world. Then I will briefly talk about quantum electrodynamics, the accurate predictions, what's that? Inaccurate predictions. Quantum coherence, wave nature, free coherence, particle nature, wave particle duality, and the active light. Marks and interferometer, which probably you may not get a feeling about what I will talk about, but we have done this. In some people, delay choices. There's something very interesting actually, this delay choice entanglement. It's mind-boggling. Then I will talk about transit experiments, which will be in detail. I think Professor Kennagon spoke about it. Then there's something called delay choice experiment also on that. Okay, nature and reality. First, I will give you briefly what I think actually, and this is also scientific fact. The first one is how we perceive the world. Visible. You know, visible EM radiation falling into your eyes, you perceive as vision, before vision. But, I'm sorry, this is covered by some image, okay. But the thing is, you do not see it with your eyes, but with your brain. The best examples are visual illusions. You have experienced a lot actually visual. That means you don't feel the radiation, but your brain creates an image. That is what you see. In the same way, variation in pressure, the air. You perceive as sound actually, pressure variations. But you do not hear it by ears. You don't hear the pressure, but hear it here. Brain creates sound, a sensation of sound. Then again, the same thing is true with your tongue, chemical reactions, chemicals, not just their tongues. Then chemicals address the tongue, then you perceive it as taste. Same thing is the smell. Then you may wonder why it's relevant. Because what I am telling you is that even though we see the world as it's a reality as this, what I see and what I hear, there's something there actually. This is created by our brain. So there can be so many things surrounding us which we do not perceive because we don't have senses. One of the example actually I want to talk about is these migrating birds. These birds, there are two types actually. Here there are thousands of birds, a variety of birds. They travel thousands of kilometers from their breeding grounds to winter grounds. Then the question actually scientists worried about is how they find their way. How they find the basically same area every year, again and again. Then when the new birds are born, you also find the same. people knew that they follows Earth magnetic field. But it was very vague, actually, until recently. They did not know how. Now, what they know is those birds' eye have it's like a magnetic sense. Magnetic sensor is formed with their eye actually when certain frequency of light falls into their eyes. That the eye gets some chemicals in the eye, generate radical pairs. That means radical means they have extra electrons. Then electrons, I think you know that, have speeds. They are paired. Then sometimes, oops, this is not a, that's not right. I can show mouse or something. You can see these speeds. Those electron speeds, those radical pairs. What they found was they switch. Sometimes they become anti-parallel, sometimes they become parallel. Spin can have, spin-off particles can have certain in any direction they can have spin up and spin down. In this bird's eye, the chemical pairs, those two switches over 1 million per second. Then that frequency, it lasts about, sorry, I remember 1 millisecond. Even though the Earth magnetic field is so weak, that can interfere. That switching back and forth. That is what birds feel, sense. Then the question is this. It is a new sensation. We never experienced. We don't think that is happening in our eyes. Then what I want to tell you is that we don't know what kind of a sensation they get. It is not sound. It is not light. Complete different sensation. That's the whole thing. Because that means that quantum physics, you don't have to understand. You don't have to understand the quantum physics with our senses. That's the thing. Or classical. We don't have to understand it classical. Okay, I will get into the subject now, actually, first one. My talks will contain certain slides which are somewhat technical, some others are non-technical. Please don't get offended by questions and the things. I will briefly describe what they are. And I think, again, I hope you know that the elementary particles, how it speaks. Unfortunately, I cannot aim this and show it because I can't get in this camera. You can see this. Second, yes. Excuse me. I will briefly describe element particles. As an example, electron can have a spin. The spin means it has a magnetic moment. Then you apply a nonlinear magnetic field according to whether they are spin up or down. They will divert into 2 different places in the screen. This is this box-like thing is the electron gun. It emits electrons one after the other. Then, depending on the state of the electron, it can go up and can go down. That's called measurement. That means this way, if this electron is this observed up there, it will be plus half. Otherwise, it is minus half. Okay. Then the plus half and minus half. Forget about these arrows and arrows with this greater than sign and those are vectors actually. But you can say that they are labels representing those 2 phenomena: spin up, spin down. any general state. As an example, you can see an arrow. I put red color arrow. If okay, we know that when first I will tell you like when you observe something in this area, you know that that is a spin of particle. That is represented by this up arrow. If it is down, it is this one. Then the question comes, what happens when it is here? When it is here, in mathematically, what we do is we represent it by a it's also a question. I'm not going into detail, but this will be necessary later on. That's a very briefly. You write it this way. Those symbols are representing those spin and spin down. Then these are numbers, complex numbers. Those square will add up to 1, indicating that when you have an electron, definitely it will be up or down, nothing else. That equal 1 means that. Another thing I have to tell you that the special thing about electron, or there are other quantum properties. It doesn't matter in which direction you aim those magnets. So still you get, all the time you get plus half or minus half. That is what I'm trying to represent here. In different direction, you again get up or down, but with maybe different probabilities. These are mod squares, indicates probabilities of finding up electron or down electron. That's all. Because these will be necessary later on to describe certain quantum effects. Then the question comes, we talk about birds and our eyes. How do we perceive that? So the question of room space. I have seen in the internet, so many people are describing the particle is in both directions. They say particle in both states. I don't think that is the correct way of visualizing it. Only thing is we don't know what this looks like. Actually, we may see it, but we don't perceive. That's what I want to tell you. Because our brain is limited, but the brain maybe couldn't make any sense out of that. Okay. I will tell you about the what we call best prediction of quantum physics and worst prediction. This is under quantum field theory, as perhaps I think Ponnamperuma mentioned. The quantum field theory was developed to make the quantum physics consistent with specialty of relativity. That way, they become Lorentz linear. So QFT, special first theory they developed was quantum electrodynamics. That is theory which describes how light interacts with matter. That was actually considered as the most accurate theory in physics. You will see why. One of the most accurate prediction of QED so far is the electron's magnetic moment. The electron's magnetic moment is often described in terms of something called G factor. Only thing you have to think that G factor is something you can theoretically predict, and the value of it you can theoretically predict and experimentally measure. It's called it is the relationship between particle magnetic moment and its angular moment. Theoretical value prediction from quantum electrodynamics is this value. G over 2 is this number. Actually, this to predict this, they have assumed something weird. Something is that vacuum state in quantum physics. That is, vacuum is not empty. That way you predict it. This is the experimental result. Actually, this is the latest one in 2023. You can see, if you check this, those two agree to 13 significant figures. These two is one of the most accurate thing predicted and observed. Great. Then actually everybody is happy, then I will give you another side of the story. This is the most inaccurate prediction. Actually, it is not a quantum prediction in a certain sense, but if we try to predict it, this one. When Albert Einstein developed general relativity, we wrote down the equation. You don't have to worry about this equation. But in the equation, there is some constant there. It's called a conspiratorial constant because that affects the lot of properties of the universe. Then when the people measure them and when we predict actually, you will see, in quantum physics, vacuum itself should experience quantum fluctuations. As I said, it is not energy. It contains energy, especially radiation. Actually, it's the problem is not only quantum electrodynamics, all the other interactions have their own vacuum. Then all the vacuum add up. That vacuum energy is huge. According to this equation, this part is the energy part, energy moment tensor. Whenever there is energy, that affects this equation. What happened was, when they found that this calculated vacuum energy density is many orders of magnitude. You don't believe the first day to found it. It is like, say, experimentally, theoretically predicting it is 1. But the answer you are getting is 10 to the minus 120. Or actually recently, the value came down to 10 to the power 60. That means if you assume the theoretical value is 10 to the power 60, then the real experimental number is 1. So it's a huge error. So there's something big from somewhere. So I thought mentioning this is based on Wikipedia. This is called the cosmological constant problem. People have been trying this for so many years to solve this. Here again, I give you very briefly something actually relatively new, maybe last 30 years or something. We never learned these things in university also. It's called how the people are doing operational quantum. What happens is whatever we learn in the quantum mechanics in the university are actually belongs to this middle box. I will very briefly tell you what this is actually. This describes a quantum experiment. What you do is, in the first box here, we prepare some particles. It can be electrons, cadmium ions, whatever, cadmium atoms, whatever, protons, whatever, we prepare. Then we can prepare to in a certain state. But the problem is with this system is, we experimentally, we cannot produce it perfectly. As an example, if you try to produce a spin up particle, you may get most of the time a spin up, but once in a while you will get something slightly different from up in a different direction. That's why this rho thing comes. Now the more fundamental thing is called density operator. That is what's more fundamental than the wave function. Wave function, I think, is something like an ideal thing. It's called pure states. I'm not going into details, but here the experiment does it is, you prepare it. Then you do some transformations. That means you apply a magnetic field or whatever. The experiment you do. Those are called transformations. You do something to this rho, then you will get a new rho. Then as a measurement, when you do something, you measure something, you do it here. Again, measuring your outcome of the experiment will depend on the status of this box, what to measure it is. I added another line, which is again, don't get offended, don't get. I thought something because to describe something which may be useful to you, something this technical. For these are called pure states. you can define the density operator by this taking this whole mathematical out product. The important thing is this. These represent this one H and V I use for the horizontally polarized light and vertically polarized light. What I want to tell you is that when you see these things, remember, I don't know whether you have come up across the coherence, the proportions, and the coherence. These middle two terms represent something like wave like thing in the quantum systems. These two are like more classical, A and B, these two. What happens is sometimes when you have transformations, due to interactions, these two becomes very, very small. Then this becomes a two-term thing, which is more like classical. So that is, people are now saying that is the way the quantum systems, the quantum systems become classical due to weak coherence. But still, it does not explain the quantum to classical transition. But it describes something. Some classical will come out of this. It's called environmental decoherence. Those are details I won't mention. Still, okay, now I'm going to the real talk. Actually, I said a lot of things in background. After this, I will describe the various experiments. I will find them amazing and sometimes puzzling. To describe that, first I will describe something called beam splitter. But the beams, if you are not familiar with this, what happens is if you have say some laser light, this is the beam splitter. Okay, this small piece of say glass. When you send photons, light photons one by one, what this does is sometimes it transmits, sometimes it reflects that photon. 50-50 means if you send n photons, n over 2 times n divided by 2 times this detector will observe a photon. This one will do the same. That means this photon, there's an equal probability, equal probability. It can go this way or that way. That is useful. Okay, for the next one. This is again, now I'm talking about again something with particle and sorry, this. Before that, I have to mention something else. So, you can think that this until 1985, scientists couldn't make single photon sources. They cannot reliable single photon sources. Now you can buy actually. I think you can buy from especially from Colab. You can buy sources. What they did was, I will tell you how they verify it. Remember that this will take 50% of the photons this beam splitter receives, this gets other 50. To test this, what they do is this is this single particle source that will emit photons. It gets reflected this way or transmitted this way. Then what happens is you measure it. Then P1, P2, you can consider as it is measuring number of times they receive a photon. Then PC means if they receive at the same time, it's called coincidence count. If PC is 0, that means you have created a single photon source. That means at one time, only one photon comes. Okay, not 2 photons at the same time. If at the same time 2 photons get emitted, you will get some coincidence count because one can go here and one can go there. This was done, and actually this was done actually in 1985 to do the experiment. I think this professor Alan actually got Nobel Prize for that study. I think that also that included. I think that is also included in the Nobel Prize. This is the interesting thing. Suppose you have a single photon source here. It emits 1 photon at a time. That means there is a time difference between the one photon and the second photon coming. Then one can get reflected, other can get transmitted. Then these two are mirrors. Then they get this, they come in. Then what happens is you have a detector, photon detector here and here. Then what happens is you can see that whenever the photon goes to this path, it will go to B1. Whenever photon goes to this one, it will go to B2. Again, you get 50-50. That's a 50-50 probability that this receive a photon. Okay, that means if you, I will use 100. If you send 100 photons, B1 will get 50, B2 will get 50, because we know that this photon will go through this path 50 times. Photon will give you this one 50 times. And then there's an interesting thing happened. These again stages of quantum physics. Then we have to talk about what happens if you put another beam splitter here. Remember, this beam splitter also what it does is, whatever it receives, it sends 50, half of the photons this way, half of the photon this way. But when we do that, it doesn't happen actually. You always get a photon in D2 and you never get anything in D1. So it can be interpreted this way. These two paths, when this is there, it gets a destructive interference at D1 and constructive interference at D2. This can be easily derived. Mathematically, this can be derived. This always gets the photon. Then what happens if you block this? Because the question is, you know, that in this case, it seems like photons are not like a 50-50, you're not going this way and that way, because otherwise you would have got the same result like this one. Then what happens in this case? Suppose you put a detector here rather than then what happens is both will get both D1 and D2 will get photons. Not like previously. You didn't do anything, you only block this one. It changes. This is actually, I got from my Wikipedia, the next one. You will see we call the word. This. Okay, the states there. This is the situation. This is 0, this is 1. Then I will have not a cartoon, it's like a simulated thing. This is the image. Okay, it's hard to stop, so I will have to, mouse is not here, so this will have to, okay, this will go forever anyway. What you will see is this, when this is not there, you only get, you will get, it will there. Okay, it's not there. This one only get the signal. This one will get not any signal. But when you put there, both will get photons. That's all. It is like a constructive interference and destructive interference between these two. This is the really interesting part. In 1970, because this was a puzzle, actually, it's hard to imagine because these two beam splitters should divide the photons into half and half. Then the Wheeler proposed something called relay choice. What he said was, remember that when in this situation, you always D1 get whatever the photons coming through this path. D2 observe other path. But here, only D2 gets all the photons, D1 gets nothing. What he suggested was, now we are going to cheat, we are going to confuse the photon. Until it passes through this beam splitter, we do not decide whether we put a second beam splitter or not. After while it is traveling in these two paths, randomly sometimes you put a beam splitter, sometimes you don't. Photon doesn't know what you're going to do. So it should get confused. Because it is already decided that whether it should come this way or that way. So that is what happened here. This is his proposal. This was tested in 2007. There are so many experiments actually related to this one. In this experiment, these two parts, this part 48 meters long wire. But I think I have seen some papers, I think some Chinese group or some other group use satellites. That means it's 100 kilometers long, this one. So you don't decide until the last moment to put this beam splitter or not. Because if you put a beam splitter, you should get only one D2. You should not get anything in D1. But they did that, they found that you cannot fold the photons. Somehow it knows beforehand what you're going to do. Or after you did that, it went back in time and changed its behavior and that is what they observed. That is an amazing thing, and people are actually doing various people are doing this experiment. Actually, it's a very clever thing. I don't have time to explain how they created this single photon source. Then here that beam splitter or no, they do it here. Okay, so that is an interesting thing. I find interesting, and yes, again, either it is going back in time or photons can predict the future. In night time, that you can think. Okay. I briefly described the entanglement in terms of photon. You can do it very easily with electrons. Photons, you can see I have some animation here, going up and down. This represents the electric field of the electromagnetic radiation. Light means electromagnetic radiation. If it is horizontally going electric field, that is horizontally polarized, or otherwise it is vertically polarized in this case. So when you can again create this, then what you do is this. This is fine. This is called DV crystal. Again, you can buy it from Poland. What it does is this. It receives from laser, it receives photon. Every single photon, it produces 2 photons with twice lambda. The specialty about that video crystal is it will produce. Don't get offended by this equation, but it will tell you what it says. The photon is in this, 2 photons are in this state. What this says is this. Here H goes with V, H1 goes with H2, V1 goes with H2. What it says is, if you do it, now what you do is, if say you have this source, you send it to 2 people. Particle 1, first photon, this photon will be sent to Alice. Other one will be sent to Bob. What they do is they measure whether it is horizontally polarized or vertically polarized. What happens is, what this equation says, whenever Alice measure the photon, its photon, you get H. Polarization H. If you get polarization H, definitely Bob will get polarization V. That is vertically polarized. If Alice get the answer V, vertically polarized, definitely Bob will get horizontally polarized light. Bob and Alice can be far apart, something like a light years even. Somehow, nobody can predict whether Alice will get V, because it is not decided. It is in a superposition state. Nobody knows what is going to get. But whenever he gets one result, always the Bob gets the opposite result. So this is called quantum entanglement. Okay. Now I will describe the most amazing other thing. This is the one I think that Nakon also mentioned. Einstein told me against this one because you cannot communicate. These two particles should not be able to communicate with faster than light. But this experiment was done in the laboratory that they were able to do it. Even these two guys communicate with each other with the speed of light. Still, they cannot because they measured it so quickly. Even with the speed of light, these two guys cannot communicate. So it seems like it's instantaneous. They are very interesting experiment. This I have put this table for the future again purpose. This is what they do in this type of experiment. You constantly get one photon after the other. Normally, Bob or Alice will not record this. Their computers will record this electronically. This copy is so whenever Alice gets H, Bob gets V. Whenever Alice gets to V, Bob gets H. That's all. Then they are correlated. That means these are correlations. Far away far correlations. Even though whatever the Alice will get is totally random. I mean, he doesn't know. Even the photon should not be able to know about other photons coming here or not. Okay, then this is the one of the amazing thing I thought. It's called, I don't know whether I will try my best to explain to you this experiment. It's called delay choice entanglement sweating. It is this. This was suggested by Perez, Jewish scientist, in 2000, published the article here. This is the experiment. You will have two sources, like previous time. This will produce two entangled photons, 1 and 2. Source 2 produces 3 and 4. They can be source 1 and source 2 can be far away. But the important thing is the first photon will be received by Alice, other one 4 will be received by Bob. They receive them first. Then what they do is they do the measurement. Then they will get that, remember that table H, V, V, H. One of the important things, 1 and 4 are not entangled because they are not close to each other. They are different. But 1 and 2 are entangled, 3 and 4 are entangled. Then usually what they will get is totally random, horizontal, vertical. The table will be filled with completely random result. Later on, say, this means not hours, maybe 2 seconds later, 2 and 3 will be received by Victor. That's another person. He does a very interesting thing. By the way, this state is represented by these two. Again, don't worry about these symbols. The only thing you have to say, I have to give labels. So 5 minus 1, 2 is saying that these two are here, 3 and 4 are here. So the total state of the whole system is 1, 2, 3. Sorry. Okay, this is the kind of technical part. I will very quickly describe that. In this case, remember I told you that when you measure that especially electron spin, you can measure the spin in various directions. Those are called bases. Those you can consider as various bases. You try to measure it. Okay, this is I have to pull down and actually explain it very the best I can. I'm not sure that I will do. Okay. What this means actually that it's actually these states, these are entangled states. Remember H, V, V, H. There's another type of entanglement, H, H, V, V. That means if the first one will get answer H, other one also will get H. Other person get V, then the other person will get V. Actually, there are two types of crystals you can purchase from the product, this kind or this kind. So these are the states. But the interesting part is this. Remember that Alice and Bob observed with their measurements, say now. But Victor will measure his photons later on, after even these photons are destroyed. Because when you measure the photons, it gets destroyed, it absorbed by the instrument. What they found was this. This is the theoretical part. I will now start the experimental one, next one, because I need some space and diagrams. The same thing here. Same thing here. What he does is this. Again, this is a different basis. This means, because that I can show you that. Probably you won't be able to see this name. It is Alice, Victor, and the Bob. What Victor does is, so in the after Alice and Bob measured their the polarizations of their particles, you will get totally random columns. Then Victor does its calculation. This is something actually it's very striking also. I was also surprised. Victor can do something called some measurement called entangled measurements. That means when he measured those two photons, they get entangled. That's what actually this expression says. I will come to this one later. So what he does is, he does that. Or he can just measure the 2 and 3 separately, like Bob and like the way Bob and Alice did. So that is this case. This 2, 3 plus 2, 3 are those entangled measurement. That is, he made them entangled 2, 3. What happens is, when you collect the data, when you then compare your nodes with each other, or say 3 together, what they found was, miraculously, this was not entangled, by the way. He will decide whether he will do the measurement this way, entangled manner, or non-entangled manner. After that, when they compare nodes, whenever Victor did this entangled measurement, they found these two are entangled. 1 and 4 are entangled in the beginning, 1 and 4 are not entangled. That means again, these photons knew Victor is going to measure this entangled manner. If he didn't do entangled manner, nothing happened. These two are random. B and H, they are random. That is called entangled sweeping because it's called delay choice because the choice which was made whether these 2 and 3 are measured entangled manner or not, decided after even these two were observed, destroyed. But they act like they already knew this is going to happen. This is again the strange thing about quantum physics. People talk about this is going back in time and changing the result, a lot of things, but mathematically it can be understood. I'm not going to detail because this state can be written in this way also. What it says is, if this is there, you will get 1 and 2 entangled and 3 and 4 entangled, 1 and 4 are random. This says. But this expression says, whenever 2, 3 entangled, 1 and 4 get entangled. Here also, different manner. Actually, the power of experimental techniques is they were able to do this measurement. They cannot predict exactly you will get this one or this one or this one, but you will get one of these results. So that is I found him. There's another thing, it's called monogamy of entanglement. That means even though in the beginning 1 and 2 entangled and 3 or 4 entangled, whenever 2 and 3 get entangled, 1 and 2 will not get entangled. It is like they can have only one partner at a time. Otherwise, they have divorced the partner and get entangled with the other one. That is called quantum monogamy for these 2-state systems. Okay, I think this is the last set of slides. Again, I will describe a little bit different manner the double slit experiment, particles and waves. I think Prof. So explain his talk also. Again, this is taken from web video. I have the video, but I was not sure whether I was able to play this with my talk. Okay. What this is, the behavior is this: you have a single slit. You have a gun of particles, they marbles. You shoot them at the slit. Then what you get is, after a while, you get different places. You get the balls get hit the screen. That is great. That is what we expect. They introduce then double slit. Then what you get? You get two nice columns of hits directly in front of these two trees. Then let's talk about waves. This is, they consider water wave. It's a water pond. You have a single slit. Then you disturb the water and create a water wave. So it propagates and it will go through this slit and produces something like that we observe in the particle. One place, you get all the waves will hit here. Suppose now you introduce a second slit, again the water, then what happens? As you observe actually in the light of water wave, the water wave will go through both slits and get interference patterns. They get interfered. Okay, this is what happened in this water thing, but like also that's the same thing. They get interfered. That means in the middle you get a very bright line, then you get various lines, vertical lines, and slowly that this will be then decay. Intensity will be lower and lower. This is great. So then, as I think we explained also, so this is the image I want to show you. This is the image you get from water. So wave. This is true with light also. Then what happens? The electrons will go through this quickly. You shine light on this electron gun, it emits electrons, it hits a single slot. So you get some vertical line, electrons will be hit this way. You can have ejectors and release. Then what happens is, then you have four slits. What you will get is, you will not get two columns of the two columns, but you get an interference pattern. As he mentioned, you may think that, okay, that is great. Electrons sometimes behave like waves. That means if it is a wave, it can go through both slits and have interference. Then what they did was, they slow down this because now we have single photon sources. Now we can send one photon at a time. Then what happens was actually, I think you have seen in that video, it will create the same string. Okay? So sorry, same result. I have the same thing. So it will create the same thing. Then you can think that somehow electron lost its behavior and became a wave and went through both. And then what they did was this. They said, okay, now again we try to fold the electron. We are going to watch. In this case, we want to go one by one going there. We want to find out how the electron gets there at the other side, whether it went through one slit. Because in our sensors, we cannot comprehend it can go through two slits at the same time as a particle. Because it's not possible, it can be divided into. Then it was whenever you observe that which thought this is going to, it gives you the particle behavior and it behaves like a particle. So this was the case. Again, same story about this ejector test. Sorry, the photon test. Remember, we did something delators. Then people developed some experiments to delay the decision of what it is. watching whether it's going there. So what they did was they send one electron at a time, but you don't decide when to observe. But this was done in a very somewhat complicated but beautiful manner. I put these slides at the end because this involves some entanglement also. We'll show you how they did it. This again, previous from this place, this panel. This is a nice place. So, it's what if you don't know, they have very nice videos explaining various physics concepts. I will briefly describe the experiment. Yeah. See, I will try to finish this as much as possible because this will be the last few slides. What you do is this: you have a laser. A laser means again you are sending one photon at a time. This vertical line is the double slit. There's a one slit here, one slit there. After it goes through these individual slits, you put that video crystal such a way that these photons will generate two entangled photons, one in green, one in red. So the aim was this: you will send one. And now we have two photons. You will try to make an interference pattern out of, say, these two, which this green upper one and then this one. Then this is the interference pattern. This is 3D, which you are going to use for measuring interference. The other guy, you will decide whether you will observe this one, and if you don't have this one, if it reflected away, you know that it came from this pole. Then you know that this electron came from this pole. If the BS2 get the result, you know that it is came to this rate. But another thing they did was this interference pattern. This distance is very short compared to this distance. That means in this case, you don't decide until these two photons were observed here. That means already this thing happened. This thing, with this thing, you know that whether you got interference pattern or not. Already it happened. This decision is delayed. Whether, by the way, that's another thing I have to tell. I will, before that, I will show you something else. This is the one I want to tell you. As I said before, if you do it in this system, whenever you get a signal at A, you know that this green color photon came to first slit. Otherwise, it came from second slit. And if you get an interference pattern, now you know that you have an interference pattern. At the same time, you know which way the photons came. Because then what happens is when you do that, you don't get an interference pattern. You got this blurred pattern everywhere. Nothing there. Now you switch those two. Now you turn off these two and put a second beam splitter here. What happens is when you put the second beam splitter, if these two go to beam splitter, you lose the information about which way it came. What happens was, whenever you do that, you get an interference. That means this will give an interference pattern when you cannot find which way it came, automatically it does that. Although this was done very late, okay? Then maybe because actually they put this thing, then because of this, these two beam splitters, 50-50 photons went this way and this way. Then they get interference pattern here. Otherwise, you will know the which slit they came from, to which they came from. What happened was, it's an interesting one. So no person involves. These are beam splitters. That means if the beam splitter, this photon transmitted through these beam splitters, they will get an interference. If it just get reflected, they will not get interference pattern. That's what they observe. They collected all information. Whenever there's an observation at C and B, you get interference pattern. Whenever you get signals A and B, you don't get any interference pattern. So this is the end of the talk.